When you've got a highly indeterminate system such as a big moment resisting frame, and you're trying to figure out how you're going to come up with estimates of internal bending moments and shears and axial forces in columns, so that you know whether or not you've put your data into the computer model correctly, there's a lot of ways to go about trying to get approximate answers. They all come down ultimately to guessing where inflection points might actually end up being. And so there's a lot of rules of thumbs that have been used out there. One commonly is called the 1/10th rule, but it's not the only approach. All of them are stemming from the basic notion of simple little elements. Say the one we've got here in the upper left is a fixed beam with a distributed load, and when we do that indeterminate analysis, find out the reactions, get the shear diagram and the moment diagram, we find out the inflection point is about 0.21 L on the inside, coming out from the outer edge to the inside. If instead we had a point load coming in at midspan, that inflection point would be at about 0.25 L. And that works pretty well when you have beams that are in the middle of a series of indeterminate spans. What if you have one that's on the exterior, where you believe you have a fairly flexible column or a roller support at the left, you have this distributed load, and then we think we have fairly significant flexural stiffness such that we have zero rotation at the right end, then the point of inflection for that particular case is about also 0.25 L. Right? And then there's the extreme case where we have very little flexural stiffness attached to the edge of the beams, and such that that beam behaves more like a simply supported beam than anything else, in which case, of course, the zero moments are out at the very far reach. Okay? So what we find is, as we begin to add more and more spans into the system, that the sort of rule of thumb of 0.1 L isn't so bad. I mean, 0.25 is okay. That gets maybe a little bit big because you're going to get some rotation here. That's going to change what happens with the inflection points. So the sort of the approximation that a lot of folks will make is this 1/10 rule. The more spans you have, the closer that might actually be to being the way it really works. So again, key concept here are points of inflection approximately at 0.1 L of the span. Adjust location for actual situation and loading. Right? So notice this 0.1 L is a compromise between those various different scenarios that you saw, including that extreme of a pin-pin or a simply supported beam. That was all associated with a uniformly distributed load. Other loading patterns might get you about the same thing. Hard to really tell. Right? So before we charge off and use this to apply to get some estimates of what's going on here, some of the other assumptions that we want to be clear about are that the beam to column connections are rigid. Doesn't mean they can't translate or rotate, but that they are rigid, that we have moment transfer going on between the beams and the columns everywhere. Right, so if we take that approach, then with the 1/10 rule, the inflection point would be at 2.8 feet here, and then 2.8 feet, 2.8 feet, since these are common dimensions, and 2.8 feet here. And it's like having a hinge then in your beam, such that then we can go and find out what's going on with the moment diagram for that beam. So for this beam on the left then, with 2 kips per foot, then that acts as though it's a simply supported beam. We've got a shear force only on the 2 ends, and let's see, that span will be 28 minus 2.8 times 2, or 22.4 feet in the middle. and so that times 2, and then of course divided by 2, we end up with a shear of 22.4 on either end, just for that little portion. Now, of course, the shear diagram would be just like a uniformly loaded and distributed distributed beam with a moment diagram that's going to be like so. It'll be now WL prime squared over 8 for that maximum moment. So 22.4 feet squared times 2 divided by 8, and we get 125.4 kip foot for maximum moment in the middle. Right now, the moment at the over here is just going to be then, oops, let's draw the free body diagram. There's our column. We're going to have that little portion of the distributed load, and now we also have the shear. So the moment that is right next to the column, right at the edge of the beam, that particular moment is going to be equal to this shear value of 22.4 times 2.8 feet plus then the effect of the distributed load, which won't be a lot, but it will be non-zero. Right, so W times that little portion of L times that L over 2 for the moment arm, just for this little portion here. And so that will be 22.4 times 2.8 plus then effectively 2.8 squared, or 70.6. And so the moment diagram then for that beam is going to look, is going to be second order. It's going to be minus 70.6 on either end, and then it's going to go up to a max of 125.4, and that will be second order, like so, where we've got our inflection point at 2.8 feet, 2.8 feet, and that middle is 22.4 feet. That'll be the moment diagram that we end up with for the beams. Now for the columns, note that we get a setup that's going to be something like this, that you're going to have then this moment coming from the top, 70.6, and you're going to end up with some sort of moment down at the base. Right now, with this kind of setup, if the columns are all identical, that's really kind of one of the assumptions of the frame. Beam to column connections are rigid, and we have identical columns, at least symmetrically placed in our model. And so that means this thing is not going to sway back and forth, and so we should anticipate a moment at the far end. The deflected shape of this thing is going to look something like this, and we don't know this y yet, but that moment at the far end is going to be half, so 35.3. We'll have shears going in the opposite direction, and indeed divided by that 18 foot high, that will turn out to be 5.9 kips. Okay. Right, we know a little bit of that from the portal method and approach, and I'm going just sort of right to it at this point in time.